Welcome to The Explainer. I am absolutely thrilled to have you here today because we are about to unravel one of the most elegant, mind-bending scientific mysteries of all time. We're going to look at an experiment so profoundly simple that you can literally do it on a tabletop, yet so utterly strange that it completely shattered our understanding of the universe. But before we get to the physics, I want to pose this question directly to you. Who was the man who decoded the Rosetta Stone, mapped the human eye, and unlocked the deepest secrets of the universe? Today's journey starts not with some modern quantum physicist, but with a largely forgotten genius from the 18th century. Okay, let's dive into this, because you've got to hear about these staggering childhood feats. Thomas Young, who is often called the English Leonardo, was a true polymath. I mean, he could read fluently at age 2. He read the Bible twice through before he was 4 years old. By 5, he was learning Latin, and by 13, he had mastered over a dozen languages. We're talking Greek, Hebrew, Italian, French, and Syriac. Oh, and if that wasn't enough, he grew up to become a medical doctor in general practice. So his credibility and raw intellect were simply off the charts. To give you an idea of his incredible range, consider the famous Rosetta Stone, which was discovered in 1799. Scholars were completely stuck trying to decipher its ancient symbols. But in 1814, it was actually Thomas Young who translated the Demotic script and became the very first person to crack the code of these Egyptian hieroglyphs. And this brilliantly illustrates how his genius extended directly to medicine and human anatomy too. He discovered astigmatism, and he definitively proved how the eye focuses. He actually did this by immersing his own eye in water to neutralize the refractive power of the cornea. Yeah, that proved once and for all that it's the internal crystalline lens that changes shape to focus light. Section 1, the wave versus particle debate, a century-old scientific mystery. Now, while his medical and linguistic feats were absolutely astounding, his greatest battle was actually in physics, where he went head-to-head against the legacy of none other than Isaac Newton. Newton had famously theorized that light was made of a stream of tiny particles, or corpuscles. For 100 years, nobody dared question Newton. Well, until Young, who firmly believed light was a wave. To prove it, he invented the ripple tank. By using a vibrating elastic wire hitting water, he studied how continuous waves spread out and interfere with one another. He then took this wave concept and applied it to light. He hypothesized that if light were just a stream of particles, shining it through 2 narrow slits would leave 2 simple, bright lines on a screen. But when coherent light actually passes through 2 slits, it doesn't create 2 simple lines. The light waves spread out from the slits like ripples in a pond, overlapping to create this beautiful interference pattern of alternating bright and dark fringes. This was undeniable proof. Light behaves as a wave. Section 2, double-slit geometry explained. Decoding the mathematics of fringes. Let's move to and see how this builds into the actual geometry of how this incredible phenomenon works. Now, don't worry, we are going to walk through this step by step. Imagine 2 coherent light sources, our 2 slits, separated by a tiny distance we'll call d. The light travels horizontally across a much larger distance, d, to hit a screen. If we look at a specific point on that screen, let's call it point Q, the light wave from the bottom slit has to travel a slightly longer path to get there than the light from the top slit. Because of the geometry formed by the slits in the screen, this extra distance, the path difference, is mathematically equal to y times d divided by d. So the crucial point is this magnificent little equation right here. The fringe width, which is the equal distance between any 2 successive bright or dark fringes, is represented by w. It equals the wavelength of the light, lambda, multiplied by the screen distance d, divided by the slit separation d. This single mathematical relationship links the visible macro world directly to the invisible micro world. And here is exactly why we see that pattern of alternating spots at all. When the path difference is an exact whole number of wavelengths, the waves arrive perfectly in phase. Peak meets peak. They amplify each other, creating a bright fringe through constructive interference. But if the path difference is a half wavelength, they arrive perfectly out of phase. The peak meets the trough, literally canceling each other out completely to form a dark fringe, which is destructive interference. Section 3, in the laboratory, measuring wavelength in the real world. So, how do we actually use this brilliant 19th century math today? Let's step into a modern physics lab at St. Lawrence University to see exactly how students use Young's setup to measure the invisible. Students use a Cornell slide, which contains pairs of incredibly narrow slits. Because the slits are way too small to measure directly with a ruler, they place the slide into a projector and shine it onto the wall. By using vernier calipers to measure the enlarged projected distance and comparing it to the projected overall length, they can use a simple ratio to find the exact microscopic slit separation. Next, they fire a helium neon laser through the slits. They mark the central bright spot on the wall as n equals 0. Then they meticulously mark the centers of the surrounding bright spots, n equals 1, 2, 3, and so on, and measure their distance x from the center. Now, what's really interesting about this slide is that if you plot these distances against their order number on a graph, you get a beautiful, straight line passing right through the origin. And just a quick, lighthearted public service announcement from the lab manual: when you're working in the dark, mapping out laser spots, use your flashlight properly. Seriously, don't leave it shining face down on the black lab benches, or you're going to drain the battery and leave the next class totally in the dark. To summarize this elegant lab process, you basically plot your fringe positions and find the slope of the line. Because we know from our earlier geometry that the slope equals lambda times d over d, we just rearrange the formula. By simply measuring distances on a wall with a ruler and a pair of calipers, we can calculate the exact nanometer scale wavelength of red laser light, and even calculate the uncertainty of our measurements using standard error. It's just brilliant. Section 4, the quantum twist, when reality breaks down. Now, just when you think you have the universe completely figured out, just when Thomas Young beautifully proved that light is a continuous wave, the 20th century arrives and the plot completely thickens. Here is the massive paradigm shift. Modern quantum mechanics revealed that light actually consists of discrete, individual packets of energy called photons. Light isn't just a wave. It exhibits wave-particle duality. It is somehow both. So this begs an incredible question. What happens if we perform Young's experiment, but we turn the brightness down so low that we fire single photons, or single electrons, through the slits, exactly one at a time? What do you think happens? The results are absolutely mind-bending. When you fire single particles, they hit the screen at discrete, individual points, exactly like a particle should. But as you fire thousands of them over time, those random individual hits magically build up the exact same wave interference pattern of alternating bands. This means a single particle acts as a probabilistic wave, literally going through both slits at once and interfering with itself. But wait, it gets crazier. If you place a tiny detector at the slits, just to peek and see which slit the particle actually goes through, the wave pattern completely collapses. It vanishes, and you just get two boring lines on the screen. The particle literally stops acting like a wave simply because you watched it. Which leaves us with this staggering final thought. If the simple, passive act of observation collapses the wave function and forces the universe to change its behavior, what does that say about the ultimate nature of our reality? I'll let you sit with that one. Thanks for joining me on this explainer, and keep questioning the world around you.